Okay, so we have solved this problem. Next, in last lecture we derived the steady flow energy equation, right? And what is the basis for derivation of the steady flow energy equation? Two important things we talked about. One is the which balance? Hello. One we call as a mass balance and second as the energy balance, right? And using those two equations, we derived the steady flow energy equation. And we learned how to write the steady flow energy equation on per unit time basis and per unit mass basis. Equation number 10 and 11. Correct? Now moving further, we'll see the applications of the steady flow energy equation to the special devices like nozzle and a diffuser, maybe turbine, pump, compressor, any flow device. How you will apply the steady flow energy equation for that. This is what we are supposed to look at now. So right now we will take into account these two devices, nozzles and diffusers. Fine. What is nozzle and diffuser? Just see the definition of nozzle and diffuser. So what is nozzle? Just read the definition. So it is a device which increases the velocity or kinetic energy. This is important. A device which increases velocity and in turn kinetic energy, because if it increases velocity, let us say c1, then by default this c1 square by 2 or mc1 square by 2 is going to increase. So a device which increases velocity of a fluid at the expense of its pressure drop. So what happens in the nozzle is the pressure will drop, the pressure will decrease, and this pressure drop is converted in terms of the increase in velocity, right? So for example, I can have this type of nozzle where the cross section at the inlet is more compared to the outlet. Consider this as outlet. So what will happen is when the fluid enter at the inlet and will flow in this direction, as the area is reduced, you will find that there is increase in the velocity of the flow, and simultaneously there will be decrease in the pressure as well. Okay? Because that pressure energy is actually converted in terms of the velocity energy or kinetic energy. So that type of device we call it as a nozzle. Now what is diffuser? So in case of diffuser, what happens is this can be thought of as exactly the function of diffuser is exactly opposite to the nozzle. So what happens in diffuser is it increases the pressure of the fluid at the expense of its kinetic energy. So in case of diffuser, kinetic energy is converted to the pressure energy. Clear? So exactly opposite might be happening in the diffuser. Fine. Look at the diagram now on the right hand side. So this is a typical diagram for a convergent, divergent nozzle. So let us say this is a convergent divergent nozzle. Up to this point, this portion is called as a convergent cone, where the area is reducing, flow area. So this is called as the throat of your throat of the nozzle, and after this again the area is increasing, right? So this is called divergent cone of your nozzle. So that's why convergent divergent nozzle, or simply you can call it as a CD nozzle also. Clear? So section 1 is the inlet to the nozzle, 2 is the exit to the nozzle. And what is shown by the dotted line is nothing but our the control surface, and the volume which is enclosed here, we call it as a control volume. We know this. And the interaction happening is with the between the fluid, this control volume, and the surrounding is shown here. So we have only one inlet for this nozzle and one exit. So that's why mass flow rate is taken as m dot at in as well as m dot at out. Correct? And apart from this, whatever you see, this is nothing but the insulation. So this part is the insulation. So it means the heat rejected or absorbed from the surroundings by this system is 0. So we will start with our basic equation, which is the steady flow energy equation on rate basis. So I am taking equation 10, So we know this. We have derived this equation for a single stream of flow on per unit time basis, right? So I am starting with the basic equation, and now we will apply this concept to this kind of a nozzle, and we'll simplify this equation further. So how it is simplified? Now for this case, mass flow rate is m dot. So I have written it here. Now there is no heat loss to the surrounding, so that's why this d bar q by dt term is 0, because insulation is applied all over the nozzle, so this term must be 0, right? Then the nozzle is not a work producing device, so there is no work extracted when the fluid flows from inlet to exit, right? So we are not extracting any kind of work like expansion, right? Or we are not giving any kind of work also like compression. So this term, the work term d by wx by dt is also 0. Clear? And if I take any random datum like this is the datum. So the elevation of inlet as well as outlet is also one and the same. So Z1 is equal to Z2. So I can put this condition as well. And when you put these four conditions in equation 10 and simplify it further, it will look like this. So this term will go out, then these two terms will go, presenting Z1 is Z2, this is 0, 0, 0, right? So what remains is only these two terms, the enthalpy term and the kinetic energy per unit mass term, right? So even this will go out, mass flow rate. So the simplified form of the steady flow energy equation for a nozzle will look like this. Correct? Hello, is it clear? Note down this equation. So it doesn't mean that we will directly start with this equation. Huh? So sometimes, let us say, if they give you the situation where there is no insulation applied to the nozzle, and the heat is lost to the surrounding, let us say, or heat is absorbed from the surrounding by your system. So in that case, you should not ignore this part. So this is in general how we derived for this situation. Correct? So I would advise you will always start analysis from the equation 10 or 11 all the time. So don't just come to the conclusion, or don't directly use this expression as it is. Fine. Now can I go to next slide?
Yes.
Okay. Moving further, there is some problem. Let it be. So application of steady flow energy equation to a throttling device. Now what we mean by throttling device and how to apply the steady flow energy equation here. So when a fluid flows through a constricted passage, so you must have seen if you have a pipeline like this, and let us say you have some valve in between, right? So depending on the position of this valve, you will open it partially or maybe fully, or you will completely close the valve, right? So when you open the valve partially, what is happening is the flow is constricted, means you are restricting the area through which the flow is passing or fluid is passing, right? So that type of device I am talking about. So when a fluid flows through a constricted passage, like partially open valve or an orifice. Now what is orifice is you can have the pipeline like this, and if you attach one disc here in between, having this hole drilled at the center of this disc and attach it inside the pipeline. So this kind of configuration is called as an orifice. You will study more about orifice in fluid mechanics. So only thing is, remember the flow area is constricted here, so it will be almost half of the diameter of the pipe. This diameter is half of the diameter of the pipe, so area will be reduced here, flow area. So if the flow passes through the orifice like this or a porous plug, so porous plug is something like you have the resistance for the flow of the fluid. Like you have a sponge and there are some porosities present inside, and they will resist the flow of the fluid through it, right? So there is an appreciable pressure drop in these kind of situations. So when you have the half open valve, there is pressure drop happening at this point. Same is true about the orifice and the porous plug as well. And the flow is said to be throttled. So this type of situation, we say that the flow is throttled through that device, right? So how you simplify the steady flow energy equation for this kind of device, throttling device. So again, I'm starting with the same equation, which is equation 10, right? So this is the typical diagram for the valve, and how it is opened partially, and how it resists the flow of the fluid. So for us, we should understand this is the control volume. This is dotted line. This one is the control volume for us, and flow is entering at this end and leaving at this. So we call this as section 1-1, section 2-2, and again, if you observe, this valve is insulated from outside. So the moment you see insulation, it means this term is 0. This term is 0, right? And again, this is also not power producing or power consuming kind of device. So this term will also go to 0. So this is the simplification now. So mass flow rate, you will keep it as it is. Reason being, it is only having one inlet, one outlet. So mass flow rate is m dot. Just now I talked about the insulation. So this term is 0. It is not a work consuming or work producing device. So this term is also 0. And again, if you take the data, Z1 is equal to Z2. So the simplified form of the equation will look like this now. Now there are two possibilities in this. You can consider the changes in potential energy, or you can ignore it, right? Or you can simplify the equation similar to the previous case. So you will get the same equation which you have derived for this nozzle or diffuser, right? So the simplified form of the steady flow energy equation will look like this. So where we have neglected the changes in potential energy, or we have simply assumed that Z1 is equal to Z2 here, right? Now, if the changes in kinetic energy are small and neglected, so it means I can simplify this equation further. If C1 and C2, these are very small values or very small quantities, like if the flow velocity is, let us say, 0.1 meter per second or 0.05 meter per second, something like that. So I would say the flow velocity is very small compared to, let us say, the enthalpy of the fluid, right? So comparing these two terms, if this is very small, I may neglect the flow velocity on both sides. In doing so, I am actually neglecting the changes in kinetic energy, right? So if you do that, the simplified form of the steady flow energy equation is, for the throttling device like this, the enthalpy of the fluid remains constant. So this is called as, sometimes you can call this process as an isenthalpic process, because enthalpy remains constant. Clear? So just note down these two equations and we'll go to the next slide. Can I go to next slide?
Yes, sir.
Fine. Now, next, application of steady flow energy equation to the device like turbine and compressor. Now, remember, turbine and compressor, or the turbine and the engine are, we are going to talk about 4 devices: turbines, engines, compressors, and pumps here. So first 2 devices, that is turbine and engine, are power producing devices. So there you will get work output. Whereas the devices like compressors and pumps are power consuming devices. So here your system needs work from outside. So these are work consuming devices. Correct. So work done will be, per unit time will be positive in these 2 devices, whereas it will be negative in these 2 devices. Clear? So for the sake of understanding, you can see the turbine which is shown here, and there is one inlet where the mass flow rate m dot will enter here, and this fluid will be expanded in the turbine, and this is how the work is extracted. So that work is shown here, right? So I can write it like this d bar w by dm. Now I am using this equation 11. Reason being, I already know that there is only one inlet and one exit, and I want to use the second form of the steady flow energy equation, which is per unit mass basis equation. Correct. So that's why you do not see this mass flow rate term here, because it will get cancelled out from equation 10, and this is how you have simplified equation 11, correct? So we have the inlet here, the outlet here, or the exit here, and again the insulation is also applied. The moment I say insulation is applied, it means this term is 0. Or if I talk about the rate equation or per unit time equation, then this term is 0. So same way, for this I am getting the work out of this turbine, so that's why this term is positive. Or if I write in terms of per unit time basis, then I should write it like this. So this term exists here, so that's why it is written as it is, not equal to 0. Fine. So how will simplify equation 11 now? Now look at the simplification. So we know that mass flow rate is same, so I have replaced m1.2 by and m.2 by m.cp. And I already talked about this. The insulation is applied, so this term is 0, correct? And the elevation. So if you take any random this datum and you try to find out the elevation difference between two, inlet and exit, and if it is negligible, I am going to assume this Z1 equal to Z2. If it is not negligible, we have to consider this, remember. So time being, I am saying that it is equal, more or less equal, so Z1 is equal to Z2, right? Now, the changes in potential energy and kinetic energy are small and can be neglected. So I may neglect the changes in potential energy and kinetic energy, and these terms will also go to 0. All these terms will become 0 because I am neglecting the changes in potential energy and kinetic energy. So there is one typing error here. I should write this as d bar q by dm because I am using the per unit mass basis equation. So make it d bar q by dm, do this correction. This must be equal to 0. So this term will be 0, and the simplified form of the steady flow energy equation will look like this. So the H1 is equal to H2 plus d bar Wx by dm. So this is the simplified form of steady flow energy equation when applied to a turbine. Is it clear? So if I say or if I make a statement that this equation is applied to turbine, then I would say the work is obtained from the turbine at the cost of decrease in enthalpy. Getting me? Work is obtained from the turbine at the cost of decrease in enthalpy. So I can write H1 minus H2 is equal to d bar Wx by dm. No? So this itself indicates that the work is obtained in the turbine at the expense of decrease in enthalpy. Now if I apply the same expression to the device like compressor or pump, so what will happen there is, there will be increase in enthalpy because work will be given as an input to the system, right? So whatever work you will apply to the system in case of compressor or pump, it will help in increasing the enthalpy of your fluid. Understand this? Whereas same equation is applicable for the compressor and pump as well, but in the reverse sense. So when you apply this equation, let us say you know H1 and H2, then for turbine you will get this term as positive, but for compressor and pump the same term will become negative because you will have to give input work to this device, compressor or pump. So note it down this equation. Now can I go to next slide? Okay. Now the last device where we'll try to apply the steady flow energy equation or try to simplify the steady flow energy equation. This device is a heat exchanger. Heat exchanger. You have separate module on this topic, heat exchanger, in the 5th semester when you study with the subject of heat transfer. So you will study in detail what are different types of heat exchanger and all. So right now we are only considering this as a simple steady flow energy, steady flow device, right? So what is heat exchanger basically? So it is a device in which heat is transferred from one fluid to another. So the only requirement of a heat exchanger is you should have two fluids exchanging the energy with each other. That is the only requirement. So you can have a very simple kind of heat exchanger, like take two concentric tubes like this. This is the inner tube and the outer tube, right? And just pass hot fluid on one end, maybe let us say through the inner tube in this direction, and pass the cold fluid in the this passage of these two tubes, the outer surface of the inner tube and this passage. So pass the cold fluid through this. So these two fluids will interact with each other, and there will be the heat transfer taking place from hot fluid to the cold fluid. So this can be thought of as a simple heat exchanger, which is called as a concentric tube heat exchanger. So what is shown here is some kind of a complex situation. I have explained you in simple way here. So look at this heat exchanger now. So what you see is there are two fluid streams. One is the steam and another is the cooling water, right? So section 1.1 cooling water is entering through this passage, and it will enter through the tubes. These are the tubes. So through the tubes the water will enter here, cold water, and or the cooling water, and the cooling water will come out from this passage and will go. So the mass flow rate of cooling fluids, that's why, or cooling water, so m dot c. So same time you will see from top to bottom there is the flow of the steam. So the exhaust steam after doing the work of expansion in turbine will be passed through this kind of device like heat exchanger. So it is passed here, and now the steam will come in contact with the cold fluid which is flowing through the tubes, and the steam will get condensed because heat will get transferred from this condensing steam to the cold fluid, and this is how the cold fluid will become somewhat hot and will go out from section 33. Whereas steam which is entering at this section having the state as the steam or a vapor will get condensed, and the condensate or the water will be collected in this tank, and it will be passed on further, right? So that's why this is mass flow rate of the steam m dot s is through section 2.2 it will be inlet, and here it is outlet. So this is simple flow device, we call it as a heat exchanger, where there are two fluid streams exchanging heat with each other. Now I am starting with the basic equation 10, and I will try to simplify this same equation. Now how you simplify this? So in case of this heat exchanger, we know this is not a power producing or power consuming device. So you are not giving any energy input to this device to run, or it is not giving any work output also. So this term will become 0. Correct? And if I say or if I make an assumption that there is no interaction, heat interaction with the surroundings, so whatever heat interaction is taking place is only between these two fluids. So one is losing the heat and another is absorbing the heat, right? So it means this term will also be 0. So to the surrounding, this d bar q by dt, or from the surrounding, this d bar q by dt, these terms are 0. So this is also 0. Correct? Then if you say that there are no the flow velocities or flow velocities are very small, so you can neglect those terms, right? These terms, and after simplification you will get this kind of equation. Now I have not added two terms here because there are two fluid streams, right, which are entering the control volume, means this one for the cold fluid in and the steam in, right? So I should add one more term here which is not written here. So that is considered or that is I am assuming that you already know this, that you have two terms on this side for these two inlets, and two terms like this on the right hand side, which are for this two exit, cooling water exit and this condensate exit, right? And after simplification you will get this equation. So m dot ch1 plus m dot s h2 must be equal to m dot ch3 plus m dot s h2, right? And whatever the assumptions I talked about, they are already discussed, and they are written here in this paragraph. Correct? So can I go to next slide now?
Yes.
So that's all about the basic derivation of the steady flow energy equation and its applications to the flow devices and how we simplify the basic steady flow energy equation. Correct. So in examination they may ask you to they will ask you questions like derive the steady flow energy equation and then apply it to the devices, like any device they may say, like apply it to heat exchanger or apply it to turbine or pump or compressor, something like that. So when this kind of question is asked, what is expected is you will start with the basic equation and then you will write all the assumptions which you are making in between and how you simplify this. Don't directly jump to the final form of the equation like this. You have to simplify it like this and justify why these terms are zero. Is it clear? Now can I go to next slide?
Yes, sir.
This one, 4.2. So read the problem statement carefully and try to solve this. A gas flows steadily through, this is a steady flow device. A gas flows steadily through a rotary compressor. Device is compressor. So this is compressor is power consuming device. Right. Now the gas enters the compressor at a temperature of 16 degrees C, a pressure of 100 kilopascal. So if you say state 1 as the inlet and state 2 as the exit, so then this is P1, pressure 1 is given, 100 kilopascal, and an enthalpy of 391.2 kilojoule per kg. So H1 is also given, specific enthalpy, it is per unit mass. So the gas leaves the compressor at a temperature of 245 degrees C. We know in doing compression of the gas, the temperature will rise. A pressure of 0.6 megapascal. So the pressure attained after compression, this P2 is 0.6 megapascal, and an enthalpy of 534.5 kilojoule per kg. So it means H2 is given, right? So because of compression, there is a rise in the enthalpy of your fluid. Now there is no heat transfer. This is important. There is no heat transfer to or from the gas. Means this term d bar q by dt or this term is zero, right? To or from the gas as it flows through the compressor, right? And number one, what you have to do is evaluate the external work done per net mass. External work done per net mass means when they are saying find out the work done per net mass, it means you have to use the equation which is per net mass basis, equation 11 and not equation 10. Get me or not? So they are asking you to find out this d bar wx by dm, assuming the velocities at the entry and exit to be negligible. So for first case, you have to assume that the velocity at inlet and exit are negligible or zero, correct? And for second half, evaluate the external work done per net mass, means again find out this term when the gas velocity at entry, this is C1, 80 meters per second, and that at the exit is 160 meters per second. So C2 is 160 meters per second. So under this condition, what is the work d by wx by dm? This is what they have asked. So what is the equation you will be using? This one. This is your equation 11. Correct? Per net steady flow energy equation on mass basis or per net mass basis. So H1 plus C1 square by 2 plus ZZ1 plus d bar q by dm. This must be equal to H2 plus C2 square by 2 plus ZZ2 plus d bar wx by dm. So simplify this equation further, right? So for first case, case 1, you have to neglect this. You have to neglect this term also. And you can assume that Z1 is equal to Z2, so this is also 0. Whenever they do not mention anything about the elevation, you can straightway take it as a 0. Hereafter, remember this, fine. This term also they have asked you to take it as 0. So when you apply it for the case 1, the equation will reduce to this form. correct? And when you apply it for case 2, you have to add these two terms, these two. So you will write the expression like this, must be equal to, sorry, h1 h2 plus c2 square by 2, correct? c2 square by 2 plus d bar wx by dm. So in both cases you have to find out this. Now one word of caution when you use these equations. So this is simple. When you use the enthalpy in kilojoule per kg here, and if you take the enthalpy difference, your answer will be in kilojoule per kg by default. But when you use this expression, it is difficult because velocity is given in meter per second, right? So the units here are not in kilo. Remember this. So what I would suggest is, you better way don't use the kilo units here. So what you can do is, for example, this enthalpy is given 391.2 kilojoule per kg. So simply take this enthalpy in joule per kg. So you can write it like this: 391.2 into 10 raised to 3 joule per kg. Take it like this. Correct? So this is 391,200, right? So if you take this in joule per kg, then this velocity will be in meter per second, and the dimensions or the units on both sides are balanced, otherwise not. So if you use this in kilojoule per kg, answer will be in kilojoule per kg, but here you have to use in joule per kg, then your answer, this answer will also be in joule per kg, and then convert it to kilojoule per kg. Or there is one more shortcut which is given in few books, which I do not recommend actually. What people have done is, they have divided this term here by 1000, so that this term will be in kilo, and then you can use these two in kilo. That is also fine. So if you do that, the equation will look like this: c1 square by, this is 2 into 1000, this must be equal to h2 plus c2 square by 2 into 1000, this must be equal to d bar wx by dm. Now this time all values are in kilojoule per kg. So whatever method you feel is suitable for you, you can adopt that. Is it clear? Hello.
Yes, sir.
Solving it or not? Answer I have already projected on the screen. You just cross check and tell me. Even though it is written W on the screen, it is actually this d by wx by dm only. First one is very simple. You have to just take the difference between these two enthalpies. So 391.2 minus 534.5, right? So this will be minus 143.3, correct?
Yes, sir.
So that minus sign indicates that this is a power consuming device. So you will get minus sign for the work, because work is not extracted here, work is absorbed by the machine. So this is expected result, that minus sign will be there. Now check for the second case, when you consider the flow velocity C1 and C2. Once it is over, tell me, we will go to next slide. You must have noticed by this time that I do not directly jump to the final form of the equation. I will always start with the basic form of the equation 10 or equation 11. And all the time I will do this, all the time. Is it correct? For second case, 1 minus 152.9. It's very simple. Hello. This is very simple numerical. You should not take more time to solve this kind of problem. I hope you are solving this. Is it over?
Yes, sir.
When you will tell me? Can I go to next slide? Say quickly yes, no.
Yes, sir.
Okay, fine. Solve this one. Solve numerical 4.3 now. Read the problem statement carefully. Air flows steadily, and this is again a steady flow device. Air flows steadily at the rate of 0.4 kg per second through an air compressor. So now air compressor has one inlet, one exit. So this is straightway m dot, mass flow rate of the air. Entering at 6 meter per second. So this is C1 with a pressure of 1 bar. So pressure P1 is given. And a specific volume of 0.85 meter cube per kg. So this is small V1, specific volumetric inlet. And leaving at velocity 4.5 meter per second. So this must be C2, correct? So this is C2, then with a pressure of 6.9 bar. So this is the pressure after compression. So E1 is 1 bar, P2 is 6.9 bar. And when you pressurize the air or compress the air, as the pressure increases, the specific volume will go down. So this is specific volume at state point 2, which is after compression. So 0.16 meter cube per kg. Now the internal energy of air leaving, this is important, the internal energy, or rather I should specifically say the specific internal energy. Even though it is clear from the unit, it is better if I mention it here. So the specific internal energy of air leaving is 88 kilojoule per kg, greater than that of the air entering. So if I say the specific energy or internal energy of the fluid entering is small u1, then u2 is the specific internal energy of the leaving fluid. So this is equal to u1 plus this 88 Now, if I am using this in joule per kg, I will write 88,000. So the unit for this specific energy is joule per kg now, and not kilojoule per kg. Is it clear? So if you want to use in kilo, then you will write only 88 here and not 88,000. So up to this point it is clear, greater than that of the air entering, right? Or you can simply say U1 is equal to 0, then U2 will be equal to this quantity. That is also fine because these two are relative terms, right? Then cooling water in a jacket surrounding the cylinder. Now, so this is your compressor, let us say this is your compressor, and this is what you can say, the cylinder wall, right? And here is your piston. So what happens because of the compression? There will be the increase in temperature of the fluid, right? So it will give away the heat to the surroundings. Now what they do is they put some kind of water jacket in this cylinder wall here. So assume this as a water jacket, and water is circulating, and water is circulating through these passages, right? So what happens? Whatever heat is generated here because of compression, that is thrown away by the air to this water, and water, this cooling water in the jacket extracts the heat from the gas. Understand this? So if I say that my system is the gas, if I say my system is gas, now this gas is giving away heat to this cooling water. So how you will incorporate that term? For that reason I am explaining this. So cooling water in a jacket surrounding the cylinder absorbs heat from the air at the rate of 59 kilojoule per second. So what is this quantity? 59 kilojoule per second. This must be now this is given in kilojoule per second, means kilowatt, or you can write 59,000 joule per second. This is watt, right? So this is heat absorbed by the cooling water. So if you say this is your system, so I would write d bar q by dt. Now why dt? Because this is in per second. So d bar q by dt is 59,000 joule per second, right? Now whether the sign is plus or minus, you know what is the sign convention? Heat supplied to the system is positive or rejected by the system is positive. I think you people are not getting what I am saying. So what is the sign for this term? D bar q by dt. See, this is your control volume.
Positive.
And this is d bar q by dt direction.
Positive.
So heat rejected by the system is positive or supplied to the
Negative.
system is positive?
Supplied is positive.
So here it is extracted or given out by the system. Na? So this must be negative na, in that case, or not? Correct?
Yes, sir. Negative.
So understand the sign convention. And then it is very simple. So you have to solve this. Calculate the power required to drive the compressor. What do you mean by power required to drive the compressor? So you have to find out this term d bar wx by dt, which is in joule per second or watt. This is nothing but the power required to drive your compressor, right? And apart from this, find out the inlet and outlet pipe cross section areas. So you have the circular pipe as an inlet and outlet. So you have to find out the cross section area A1 and A2. So A1 will be this pi by 4 D1 square, right? And A2 is pi by 4 D2 square. So they are not asked you to find out the diameter. They have straightway asked you to find out the area. Of course, once you know area, you can find out the diameters also. That's fine. Last time. So this is the starting equation, equation 10. Now, can you solve it on your own now? Hello? Or shall I write the values on the screen? You tell me.
Right.
Okay, fine. But you have to help me while writing the values. So this term we'll write first one. M dot one is 0.4, right? Into bracket. What is the enthalpy now? H1. Find out the enthalpy H1. So can I write it like this U1 plus P1 V1? We know this. So I am going to write this enthalpy H1 as U1 plus P1 V1, right? So now you tell me, shall I use values of enthalpy in kilojoule per kg or joule per kg? Accordingly, I will modify the equation. You tell me.
Kilojoule.
Okay, so you want to use in kilojoule per kg. So I will write the equation in this context now. So if you want in kilojoule per kg, so I am saying, let us assume the initial enthalpy of the fluid entering the this compressor. I can simply say this as a 0, and then U2 will be equal to this value in kilojoule per kg, right? So I will write it here 0 for this U1 plus pressure P1. Now if I want this value in kilo, pressure should be in kilopascal. We discussed this. So 1 bar is 100 kilopascal. So I'll write 100 multiplied by the specific volume at the inlet, which is 0.85. So this whole term is for H1, right? Now plus. Now I need this term in kilojoule per second. Kilojoule per second. Now for doing that, I must divide this by 1000. So I will write it accordingly. So C1 is 6 meter per second. So I will write 6 square divided by this 2 into, now why I multiply by 1000 here? Because we want this term in kilo. So that's why. Plus, now Z, what is the value of G? It is 9.81 multiplied by the elevation. Now nothing is mentioned about the elevation, so I can simply neglect this term and I need not have to write it here, right? They have not mentioned anything about Z, so I am simply skipping that part here. Now plus, now next term is this d bar q by dt. So this is already negative term, we know this. So I will write minus, now we want in kilojoule per second because we are using kilo everywhere. So I should write minus 59 then here, correct? So this must be equal to, now this term I am evaluating, this is 0.4 into bracket. Now what is H2? H2 is U2 plus P2 V2, right? Now we assume U1 as a 0, so U2 will be straightway 88, right? So I can write it like 88 plus P2. Now P2 is 6.9 bar. So multiply this by 100. So this will be 690 kilopascal multiplied by the specific volume, which is 0.16 here, specific volume at the exit. So this is for H2, this whole term, plus, now what is C2? 4.5. So I will write 4.5 square divided by this 2 into 1000 here, right? Plus we have to evaluate this, so we will write it as it is, d bar wx by dt. Is it clear? Now just solve for this and tell me what is the answer. Now by chance if they give you values of, let us say, z1 and z2, if they say z1 is this is only for the sake of explanation I am saying this, it is not included in this numerical. So let us say they say z1 is 3 meter and z2 is, let us say, 5 meter. So in that case, how will write this term zz1 and zz2? So when you write this zz1 term, you will write z 9.81 multiplied by z1, which is 3 meter, and you have to convert this to kilo. So divide this by again 1000, and then everywhere you can use the values in kilo. So you have to make sure that you will divide here by 1000, and for in this term also you will divide by 1000. Then and then only your answer will be correct, otherwise not. Remember this. So what is your answer now? What is your answer?
1 minute, sir.
Okay, you are solving. Fine. If I'm going somewhat fast, you stop me in between and tell me that we are going fast. Now, without solving this, I would say your answer will be negative because this is air compressor, power consuming device, right? So work is done on the system. So you will get the minus sign for the value. If you are not getting your minus sign, it means something is wrong with the data itself.
Minus 104.356.
Okay. Minus 10. I'll write it here and then we'll cross check at the end. Minus 104.8.
35356.
That's fine. 83 kilowatt, right? Kilojoule per second is kilowatt.
Yes.
Now, apart from this, you have to find out the cross-section area at the inlet and outlet, means A1 and A2. Now we know by mass conservation equation, we have derived this. I hope you know this, m dot. See, mass flow rate m dot is constant for this flow device, steady flow device. So you can write it A1 C1 by specific volume V1 is A2 C2 by specific volume V2. So we know this equation. Now from this you can take this part and find area A1 and you can take this part, it is m dot, so find out area A2, or you can take these two and still will be in position to find out the area A2. That's fine. Find out area A1 and A2 and tell me the values. So area will be in meter square. Now don't divide this expression by 1000 here. Let it be velocity will be in meter per second only. A1 in meter square and A2 also in meter square. Tell me, area A1 is, or I'll project it on the screen, just cross check.
Yes, sir.
So this is your answer, 104.4 kilowatt. Of course, minus sign will be there. Reason why minus sign I have not written is in statement itself they said that power required to drive the compressor. So even though you get minus sign here, when you write the answer, you should write it like this: power required to drive the compressor. This itself indicates that power is consumed. So then you need not have to write minus sign. So that time you will write 1.104.4 kilowatt. Answer will be like this. Clear? And the areas A1 and A2 0.057 meter square and 0.014 meter square. Correct? Okay. That's all for today's class. Let me stop the recording first.